Welcome to the prediction project. And there's lots of times in education where we want to automate a process which is going to involve some kind of prediction. Perhaps we want to predict the performance of a student on the next question so that we can intervene in some way, or we might want to predict whether a student is going to drop out of a course or program so that we can intervene. There is a lot of fertile ground in this area around in both research and products and organizations that are trying to do this. On the left, we see the now famous MOOC retention graph published by the Open University in 2013. MOOCs tend to have very poor retention, and so there's a lot of work that goes into trying to predict who is going to drop out of a MOOC and what could be done to prevent them from dropping out. But there's lots of other services such as Summit Public Schools that have a partnership with Facebook to predict student trajectories. Carnegie Learning has a lot of intelligent tutoring systems, and there are nonprofits such as the Systems Foundation that are very interested in predicting student performance. This is where we're going to start to move into the wonderful world of machine learning. And here, what I'm trying to say is that machine learning is slightly different, perhaps, than the quantitative research that you might be used to, where you take a model and apply that model to input and output data. So you might be interested in the relationship between grades and dropping out. So you might try to apply a model that predicts dropping out from grades, and that would give you some information. In machine learning, what we want to do is take it the next step, which is to take that model that you've built and then try to update it with new data. So we actually continue to update the process, the structure, the model that is linking our input and output data. Another way to look at this is perhaps that in educational statistics, you might take your model and apply it to input and output data. And then that model is going to tell us something about the world. You might publish some kind of research or go on TV and say, look, the relationship between these two things, between grades and dropping out, is negative, and it has a parameter estimate of this much, so that for every grade point that you get more, you decrease your probability of dropping out by X amount, and that would be perfectly fine. But if you want to actually use that system and deploy it to automate some kind of intervention, then you may adopt a machine learning model, which would be you would take that model that you just built and you would apply it to new data. And you would develop a bunch of metrics that would tell you about how well that trained model will perform on new unseen data. So we end up with two sets of statistics. We end up with training statistics and testing statistics. The training statistics we use to tweak the model to make sure that it is the best model for the data that we have. And then the testing statistics tell us how well we think our model will do when applied to new data. When we're talking about classification, so when we're trying to predict categories, often binary categories such as pass, fail, or drop out, don't drop out, we can use something called a confusion matrix. And this is very common in the news media at the moment when people are talking about COVID testing. So if we line up our observations or our actual class that we're trying to predict against our predicted class or our predictions, and we can look at how many true positives, false negatives, and true negatives we get, that tells us something about our model. Is our model very good at predicting true positives, but also it gives us a lot of false positives? Or is our model not that good at predicting true positives, but it's not that good at getting false positives or false negatives? Maybe that matters. And depending on context, we will be interested in the ratios of these things, because really it depends on the context what will matter for your individual model. In some cases, getting a true positive is great, but getting a false positive is very bad. In other contexts, maybe the false positive doesn't matter as much. For example, if we think about medical testing, getting a true positive is good, and maybe you would prefer to get a false positive than you would to get a false negative. You would prefer to diagnose someone with something that they don't have than miss a diagnosis. But it depends. There's no kind of easy, clear-cut answer. But to help us flesh this out, there are a bunch of metrics that we can derive from the confusion matrix. The first one is accuracy. And accuracy is a global measure, and it can be good as a rough first cut. It doesn't tell us anything about the true positives and true negatives. If you see here, it's the true positives plus the true negatives over everything else. And that kind of hides the true positive and true negative rate. We could be quite accurate because we get a lot of true positives, or we could be quite accurate because we get a lot of true negatives. So if we want to figure out the distinction between these two things, we can look at some other metrics. Now, unfortunately, a lot of these metrics have several names. So the first one we're going to look at here is sensitivity, or otherwise known as recall, or otherwise known as the true positive rate. And that's the number of true positives over the number of true positives plus false negatives. And what this is telling us is how good is your model at making predictions when we take into account how many false negatives it is producing at the same time. A kind of inverse of this is called specificity or selectivity, or the true negative rate. And that's the number of true negatives over the number of true negatives plus false positives. Now, this is telling us how good is your model at predicting or classifying the opposite case, and how many false positives do you get in the mix as a kind of cost to getting those true negatives. The third one we want to look at is a thing called precision, or the positive predictive value. And that's the number of true positives over the number of true positives plus false positives. And so this is telling us how good is your model at getting true positives when the cost is how many false positives are you going to get. Now, this one can be particularly tricky because in most cases you can build a model that says everyone is going to drop out, and then you would be 100% correct in terms of your true positive rate. You would capture every person who did drop out. However, you would have misclassified all the other people who did not drop out. So you could have a very good model, but with respect to true positives, but a very bad model with respect to false positives. Now, it sounds crazy, but plenty of companies try to use this as a selling trick. They will say they are 99% accurate or something crazy like that, but not accounting for false positives. So you've always got to be on the lookout for fine print around the use of just accuracy or true positive rate. The last metric we want to look at is called F1, which is what's called the harmonic mean of sensitivity and precision. And what this is doing is it's trying to give us an idea of the true positive rate relative to both the false negative and false positive rate. It tells us something about how good the model is at predicting true positives when we account for both false negatives and false positives. So these are the metrics that we're going to look at in this project, and you're going to be looking at these metrics in both the training statistics and the testing statistics. And in the testing statistics, what we also want to think about is what's demonstrated by this diagram, which is that the graph on the right has a very good prediction. This model predicts every point perfectly, but it probably isn't very useful because it's not going to generalize to other data. And we need some kind of metric which is going to tell us something about how much better or worse models are than each other with respect to their generalizability. So these two models, obviously the one on the left is probably going to be more generalizable because it's very unlikely that we get the same scatter plot with any given data set. So the model on the right will not do a good job, but we want some way to quantify that difference. And the way we do that is with a thing called cross-validation, which is to estimate how accurately a predictive model will perform in practice and to give some insight into how generalizable the model will be when we apply it to an independent data set. So if we think of the no validation scenario, we just have a training set. We are just going to train our model and we are going to apply it to the data, and then we will have no idea which one of these. We could develop metrics which say one of these models is better at predicting than the other, and in this case it will be the model on the right, but that won't tell us anything about generalizability. We've got no idea of how generalizable these models are. A slightly better version is what's called holdout validation, which is where we hold out some amount of data for training, often half, and then we can compare the two on half the data. So we train on one half of the data and we test on the other half of the data. And then we at least get some idea of how well each model will do on unseen data. And that may be good enough, but it's unlikely that it is going to be good enough because it's only really one sample of generalizability. And so it's going to be very dependent on which data are in each group. So we might end up with actually having all the data that is good for one model in the training set and all the data that's good for another model in the test set. So that's not going to be very useful to us. At the other end of the spectrum, we could hold out every single value. So we could take out every row as its independent test set, and we could run a training and test on every single row in the data. So every row would be a test and every other row would be a training set. This will be very computationally expensive, depending on how many rows we have. I mean, maybe if you've got 100 rows, that's kind of fine, but if you have 1 million rows, this is going to take a very long time to test 1 million times. So the kind of compromise between these two ways of testing the data is called k-fold cross-validation, where k is a stand-in for some number of slices of the data. So we're going to, in this case, cut it up into 5 slices, where we will take some of the data, and that will be the training set, and some smaller amount of data, which will end up being the test set. And usually it's about 75% to 25% or something like that. Maybe it's 70 to 30, something like that. But then we were going to do that again, and we are going to do it again 5 times until we get 5 training and 5 test sets out of the same data. And on each of these 5, we run our model and we've developed some metric, maybe accuracy, maybe F1, maybe precision, maybe recall, something. And we're going to take the average of all of those 5 tests and see which model performs best across all of them. So in this case, in our little fake version, the one on the left performs higher, whatever that means, this is not a real metric, than the one on the right. So the overall process now is that we do a development stage where we take some raw data, we do some pre-processing, and for everyone who did HUDK4050, you did a lot of pre-processing. Then you take your process data and you'll do a thing called feature engineering, where you're going to select the variables that you want to use. You might combine some variables as well. Maybe you'll do PCA and start using components instead of variables. And then you'll feed those into your model and you'll make a prediction. And once you've got the best model that you can on that training data, I've already separated out some test data that is going to go into your evaluation process. So now you're going to do your cross-validation. You are going to evaluate how well this chosen candidate model does on test sets. And then from that, you can draw out your chosen model that is the best model in terms of both predicting on the training data and also with respect to generalizability, and you're going to put that into deployment. You will deploy that, you will create more data, which you can then feed in again and keep iterating and improving on your model. This is very time consuming and resource intensive, and it also tends to be very specific to the population that you're working with. So there were a bunch of companies who thought that they could develop models on an individual university and then sell the models to other universities to make predictions. Didn't work out that way because even small differences in populations tended to throw the models off. And so that a bunch of those companies went out of business. In terms of the types of models, if you're interested in machine learning models, a good place to start is this book by Pedro Domingos, and he goes through the 5 big he calls them tribes of machine learning models. We're really only going to look at the symbolists in this particular course, in this particular project, but know that there are many, many types of models, but they kind of fit into these 5 categories. So we're going to be using what are called classification trees in this project, and you would probably be familiar with a decision tree where we map observations onto branches and classes onto leaves. The tree describes the data, but it can also be used to make predictions, to classify things. So in the example on the right, what we have is student states are the leaves and student actions are the branches. So a student is frustrated. If they don't ask for help, they give up. If they ask for help, they wait for a response. If they listen to that response, they may understand, but if they don't listen, then they give up. Okay, so this is the idea behind a classification tree. How do we get the machine to do it? We give the machine the input and the output data, and then the machine both chooses where the branches are and also weights those branches. So a very simple version of this. So if we are trying to classify triangles and circles, and we have 2 variables to make this classification, x and y, what we can do is cut a variable up into lots of increments and then choose the increment that splits the data so that the split is as pure as possible, is the language. So what is the split that is going to separate the circles from the triangles the best? And here it happens to be in the middle, which is arbitrarily marked as 5, because we have most of the triangles on one side and the circles that are left on the left side are pretty much together. So then we can split at 5 and say that on the split we've got 4 circles and 1 triangle, and on the above 5 split we can make a second split on the second variable, y, and there it makes sense to go at y is greater than 4, and in this case what we're going to end up with is a tree that gives us the best splitting possible of all the possible splits that we could do. Now this is just a brute force. We're trying every possible combination, and so there are lots of algorithms out there so that you don't have to brute force, so that we can save some computational power. But the basic idea is that we're going to make splits for the tree based on purity or of the leaves, and that there are many purity metrics to choose from, which we won't go into here, but if you're interested, they are in the documentation and the articles in the project. In this project, we will be relying on the caret package, which is a standard syntax for comparing many models. As you might have noticed, in R, there are many different ways to write different things. There is not a very standardized syntax, so the caret package tries to bring all these things together under a standard package so you can compare different models that have been written by different people in different ways. It also has some handy features such as generating training and testing datasets and the ability to run lots of different model types at the same time. It can also do some resampling algorithms and alter parameters to generate the best model for you if you need. And it also produces lots of diagnostic metrics as the ones that we have discussed. If you would like to learn more about caret, you can check out this URL. The specific commands that we will be using is, first, we'll be creating some training and testing datasets by using the create data partition command. Within that partition, you need to define the outcome that you are interested in from your dataset, and then you need to give it the percentage of the data that you want in the training set. You can then create both a training and a testing dataset from your data. We can implement k-fold cross-validation with the train control command, which creates a small object that will be placed inside another command, but it will define the kind of cross-validation. So first we want to say that the method is CV, which stands for cross-validation, and the number of repeats is going to be the number of folds. So here I've said 3. So this will produce a 3-fold cross-validation. When we want to train a model, we can use the command train, and we need to define the model that we're trying to predict. So we're going to have this thing, this outcome, and then all the other variables that are going to predict that outcome are going to go on the right side of the tilde symbol. We need to define the data, and then we need to input the model. And the model can be one of many types. It could be logistic regression, it could be a neural net, it could be all kinds of things, but that's where we're going to define it in the method. Then we might have some kind of pre-processing that is required. In most tree-based methods that we'll be using in this project, you always want to center and scale your data because tree-type methods tend to be thrown off by uneven scales. So if you have one variable that's from 1 to 100 and another variable that's 1 to 10, then the 1 to 100 variable kind of takes over. So you have to be careful and you want to center and scale your data. Then we're going to tell the train command what our control object is called. So that's where we define the cross-validation. And then we're going to give it a metric with which to decide what the best model is. This could be accuracy. Here, I've used CP, which is complexity parameter. So that's a measure of how complex your model is. But it could be F1, it could be any of the metrics that we discussed. Is the way that you're going to define what the best model is. Once you've trained your model, you might want to test it by using it to predict some other data. So we might want to predict our testing data, and then we can generate a confusion matrix from this prediction. In this project, what you're going to do is create training and test data, and then you're going to test 3 tree-based models, CART, conditional inference trees, and C50, using data from the University of Michigan open dataset. You're going to be predicting dropout using a whole bunch of variables that you have in there. What we're looking for is determining which of these models is the best model for predicting dropout, and then we want to be able to explain why in terms of the metrics that we've developed. So both in terms of how good the model is at predicting individual data sets, but then also how generalizable is it to unseen data. Good luck.